Hi, welcome everybody. I think the clock is a bit slow, so my phone says it's 2. Anyway, welcome back to the afternoon session. And Professor Walsh will give her second lecture of her mini course on examples of infinite groups, their ℓ2 homology and boundaries.
Okay, hi. I feel like I'm too loud. Not too loud, okay. So I really enjoyed chatting with people in between the talks about boundaries. So I talked some about boundaries, and a lot of people, or several people, talked to me about relatively hyperbolic boundaries, which I'm not going to talk about. I usually talk about that because I want to talk about something that I don't know about. So I think we're going to hear some more about relatively hyperbolic boundaries tonight, maybe in the lightning talks, and I'm really happy to talk with anybody about that if they want to talk about it. But I'm going to talk about something a little different today, which is the second thing in my title, ℓ2 homology. So I'm just going to give you an idea of the definition and what it's useful for. And then tomorrow, or for the third talk, I'll relate it a little bit to what I was talking about in the first talk. Okay, so the general, right over here. Okay. So a general principle, just before we get into the background, is that when we have a GCW complex, which you remember is a CW complex where I have a free cellular action of a countable group G on it, then I can label the cells of that by the group. By the group. So this is just a general idea, and then I'll say a bunch of stuff. So like, for example, if I have R cellulated by the integers, and I have Z acting on this cell complex, I can label that. I can pick my favorite one, which I can call 1, my favorite edge, and I can pick my favorite vertex, which I'll also call 1. And then all the other cells, maybe I can label by a squared, a -1, and then this vertex here will be labeled A. And downstairs I'll have 1 vertex and 1 edge. So for each orbit of cells, I can label it by the group. Okay, so we're going to use this general, very vague idea to get a homology of this upstairs part that's related to the group action. Okay, so now there's going to be a bunch of stuff that seems like it has nothing to do with that. Okay, so let me give you some. I was inspired by Francois and his numbering. So I'll try to have different sections. So let me just give some background. Okay, so throughout G is a countable group. If I forget, it's always a countable group. Okay, so ZG, the group ring, and so I could put another ring here. So often people put C or R. Okay, I'm just going to do Z because it's the easiest one. Okay. The group ring, okay, is the ring where I have terms that look kind of like polynomials. So they're going to be a sum where these AG are in whatever ring I'm taking my group ring over. Here's Z. And then G are elements of my group. And all but finitely many AG are equal to 0. Okay, so this is my group ring. I could do it with any group. So it's a lot like polynomials, and like a polynomial ring, I can add them just by adding the coefficients, and I can multiply by like, it's just going to equal the sum over G and G. I look at the coefficients where the labels will, when I do the group operation, will give me that element. Okay, so that'll just be like AG1, BG2. Sorry, I need another summation. Summation G and G. where G1, G2 equals G, and then G. Okay, so this is how I multiply. It's like a polynomial ring. It's very fun to play with. So group rings are fun to play with. So you can, for finite group rings, you can make them isomorphic to other rings. I won't do it now. And they get really non-trivial really quickly. For example, the Kaplansky conjecture says that G torsion free implies that, I'll just write it as QG, this group ring has no zero divisors. Okay, I don't know much about this conjecture. I think people might be working on it here. There's some experts in the audience or in the conference. All right, so they get complicated really quick. But we can expand this. Okay, so it's not complete. These are only finitely many terms. We can expand this to be a Hilbert space. So we can expand this to L2G, which we heard about in Deer's lecture. So this just equals, okay, the sum of AGG such that the sum of AG squared is less than infinity. And I'll take my AG in R just to try to make things a little easier, but normally people do it in C. Okay, so I could take the L2 of G over C, or, okay. So these are square summable functions. Okay, so note, if G is a finite group, this is just a group ring again. The group ring with coefficients in R. Okay, because I'm letting my coefficients be in R. And I have an inner product on this space. Which just equals this AG, BG. Okay, and there's an orthonormal basis. Just consisting of 1G, which is square summable, for G and G. Okay, so this is complete. So this is a Hilbert space. Okay, so on a Hilbert space, I can look at, just on a general Hilbert space, okay, we can consider okay, the bounded linear functionals. Okay, so these are just, I'll just use it to themselves. This is like B of V on, I'll make this V, it's like a vector space. So it's linear, it's just like regular old linear. And okay, and then bounded is just that lambda of x is less than C of the norm of x for some constant C. No, I don't want them to oh yeah. Yes, sorry. TIFR here. Okay. No, I think I actually want B to V. It's still linear. It still have a linear map. I think I want B to V because I'm going to be taking B of H at Hilbert space, going from H to H. Okay? Yeah. Okay. Okay, operators maybe. you like operators better? How's that? Okay. Okay. Okay, so, all right. So now we have B of H is this Banach space of bounded linear operators. Okay, so for H a Hilbert space, I want to look at B of H, the space of bounded linear operators from H to H. Okay. All right, so this is a Banach space. Okay, so recall, so the intuition you might be able to get here is that in a vector space, okay, like a Hilbert space, the dimension of a subspace is the trace of the projection map. Okay, because you can just think of a finite dimensional vector space. You can take your subspace to have be part of a basis and project onto that. And then you can change the basis if you want. Okay, so where am I? Okay, all right, so we can define an embedding. So the group ring is going to act as an operator. Okay, so we can define embedding of the group ring R of G, okay, into the bounded linear operators from L2 of G to itself. Okay, so this is the group ring. Okay, and induced by, this is going to be induced by, and then I'm going to extend, so H just takes AGG to the summation AGGH, and sometimes called the right representation. Okay, and then I'm going to extend to the rest of the group ring because this is how it's defined on each element of the group. And then I'll just multiply if there's a constant, add them if I have two of them. Okay, so these are like polynomials in these variables. Okay, so let me quickly try to give you some idea of what the von Neumann algebra is. Okay, so notice this is okay, so let me just write this definition down. I'll think about it for a second. Okay, so the group von Neumann algebra. Okay, so I have G a countable group. It'll always be countable. Okay, so and I have B of L2G, bounded linear operators. Okay, so these, this group ring is going to appear as, in this way as bounded linear operators from L2 to L2. And this is a group ring invariant on the other side. So this is a group ring invariant bounded linear operator. So the von Neumann algebra is actually a form of the weak closure of this inclusion, but an easier way to write it that's equivalent is you can say the subalgebra, so I'll call it script R of G, is the subalgebra of all the bounded linear operators on L2G, of all bounded operators okay, that are left group ring invariant. This is a group ring. I have two R's going on here. This is a von Neumann algebra, and this is a group ring. Okay, so the only reason I'm defining this is so that you can believe it's a thing. And there's, on this thing, there is a trace defined, and I'll give you the definition of the trace. And this trace is going to work like the trace does in like the trace of a matrix from a vector space to a vector space. Okay, so we have operators from a Hilbert space to a Hilbert space, which is like having a matrix from it takes a vector space to another vector space. And the trace of that matrix is going to be defined on this thing. That's the only reason I'm defining this, is so that you can believe it, sort of. And I'll give you some references where you can have more. Okay, so let's see what the trace is. Mm-hmm.
What do you mean by a bounded operator? What does it mean for a bounded operator to be left?
So like when I do the operator and then I multiply it, that commutes with the operation of multiplying on the left by the group ring. So it commutes. I don't want to get my left and right mixed up, but that's the idea. All right, so, okay, so the von Neumann trace definition. Okay, so the trace, which is only defined on this thing, is going to take these operators to R or C in general. If you're reading any book, it'll say C. Okay, and it just takes some operator T to the inner product of the identity with T of E. So notice these are both of these things are in L2G, so I can talk about the inner product. Okay, so this is the trace. You can write a trace of like a matrix using things like this, so it's not completely unheard of. Okay, and we can extend this, so so in general, we're not going to have operators from L2G to L2G. We'll have operators from L2G to the N to L2G to the N. So we'll have like a whole matrix. So in general, if I have, okay, we can extend to trace of this von Neumann trace, which depends on G, of matrices, N by N matrices on R of G to C or R. Okay, I'll just write it out over here. Although I know you're all looking at the screen. Whenever there's a screen, you always look at the screen. Mm-hmm. E is the identity. Good question. Okay, so you look at where that operator sends the identity element, and you take the inner product with that. Okay, so if this is just an element of the group ring, because remember the group ring embeds in here, this just turns out to be the first coordinate, like the A of the identity, or identity gets sent. Okay, right, so, okay, so let me just extend this, because I'm actually going to use it for a matrix. I don't want it to be confusing. A is just going to go to the sum, the diagonal sum, J equals 1 to N of the trace of the diagonal term. Okay, so if you have a matrix, it's just the traces of the diagonal entries. Okay, so this is just so you can, I'm actually going to be taking operators from L2 to the n to L2 to the n. Okay, so what's a Hilbert G module? Define that. Okay, a Hilbert G module okay, that's a Hilbert space. With a G action and a G invariant embedding. I takes V into L2 of G to the n. Okay. Okay, so now this is a vector space. I'm going to want the dimension of this image to be the trace of the projection map. Okay, so definition. V, Hilbert G module. Thanks. Yeah? Say it again. AJJ, I think. Yeah. Why is it AGG? You sum up the traces of each of the. Yeah, so I want it to send a matrix to R. So I need it to be a sum of numbers. Okay, so each of these will be an element of R. The trace of this element of, so I'll have like a RG matrix element at each one, and then I'll have a sum of numbers. Yeah, no good, it's super complicated. Okay. Okay, definition. Okay, so V is a Hilbert G module. So I have this embedding. Okay, the von Neumann dimension so this is the dimension, and I'll try to always keep this R of G going here. V is defined to be this trace in this trace I'm talking about of the projection map. And what's the projection map? So remember I have my I that takes V into L2G to the n because I'm a Hilbert module, and P is going to be the operator that takes L2G to the n to L2G to the n with the image, this I of V. Okay, so I embed it into this Hilbert space where I know how to take the dimension, and then I take the dimension by taking the trace of the projection. Yeah? Yeah, it's a Hilbert space, and it's a G invariant embedding. Yeah, Hilbert space embedding and a G invariant. The map P is projection so I have this embedding into L2 of G to the n, and I'm going to project to the image of V. Okay, so that's like a sub-vector space I'm projecting to. Okay, so let me say some properties of this dimension. Important. Okay, so normalize what you'd want. You want the dimension in R of G of just one copy of L2 of G to equal 1. Okay, so that's good. That's what you'd expect. Okay, and here's a really nice property. That is basically the only property I've ever used in practice. And that's if the dimension R of G of V is equal to 0. This is if and only if, all right, like this, if and only if V is actually trivial. Okay, so this can allow you to say, all right, I have this space that when you later on when you're computing homology, you can say, oh, this whole space is trivial. I don't actually have to compute this dimension because since the space is trivial, it's 0. Okay, and often we're most interested in whether or not the vector space is 0 or not, whether or not the dimension is 0 or not. So that's sort of like a course thing that's very useful to know. And so this fact is really helpful. Okay, and then another fact about maps. Another fact. Okay, so if I have a weakly exact sequence, so I'm not going to say very much about weakly exact, but this is sort of like the analog that it should be. So the okay, so so I have 0 going to V prime, going to V, going to V double prime, going to 0. So weakly exact means that this I so this means that I is injective. The image of I, the closure of this equals the kernel of pi. Okay, so I need to take the, in general, this is what's different from being exact. I need the closure of the image to equal the kernel of pi. And the image of pi, this is onto, this is the analog of onto. The closure of the image of pi is equal to V double prime. Okay, then the dimensions add up like you want them to. And the dimension of RG of V equals the dimension GB prime plus the dimension RG of V double prime. Okay, so this might remind you of homology, this exact sequence stuff, okay? And we are getting ready to define, I'll say a little bit about homology. That's all I'm going to say about the von Neumann dimension. Just remember those facts. I might say some more facts about it. Yeah.
When you say when you're writing dimension of L2G equals 1, you're doing L2G as a G module.
Yeah, yeah.
So is the embedding into L?
Yeah, you can just embed it into itself. This embeds into L2G to the 1.
Okay, by identity.
Yeah, by the identity. Yeah. That's right. Okay, so let me say a little bit about, so 2, a little bit about L2 homology. Okay, so let me first do pre-L2 homology. Okay, so let's look, so like I was doing it before right here, let's look at cells in the universal cover of KG1. Okay, and so in general, I'll have x tilde to x like this, or I'll have KG1 tilde to KG1. Okay, and I've got this G action. This covering group is G from the universal cover. Okay, so I'm going to look at the cells in here, and I'm going to label them, label by elements of the group. Okay. And I'll try to keep, when I'm talking about a universal cover kind of space, I'll try to keep my tildes on there. But ask me if I. Okay, so the N cell, so I'm thinking about X as the universal cover. The N cells fall into finitely many, because I have a finite space downstairs, into finitely many G orbits. Okay, so I can write the cells, okay, so I can write like linear combinations of cells this way is equal to, just with coefficients in Z, with a sum of ZG, where this equals, the sum is over N, where N equals the number of N cells of, I'll just write X tilde mod G. Okay, so I look down into the, yeah, question? Yes, we can do that. That's a good idea. Let's do that. Okay, so downstairs I have, I might have changed coloring, but that's okay. Okay, downstairs I have one vertex and one edge, and upstairs I have a whole bunch of vertices. Whole bunch of edges. Okay, and I can pick one, and I can call this one 1, and I can call this one 1. And then if I have an element of, let's say, 1 chains of this R with this cell complex on it, okay? So maybe I have like 3 chains here and 1 chain here, okay? So that would be an element of the N change, just with coefficients in Z, okay? I could write that as an element, so N's going to be 1 here because I have 1 edge. I could write that as an element of the group ring. I could write it as like 3a plus 1 a squared. Okay, so I've indexed my cells by this. I can label them by the group. So something that's a chain, I can write as an element of the group ring with Z, whatever coefficients I'm in, that'll be the ring. Okay, so now I can form a chain complex. That was a good idea to do that example. And if I had like the free group, I'd have 2. Okay, so A is the, yeah, generator, yeah. So Z equals A. And I'm going to label the cells. So I labeled them all, but this cell is labeled 1. This cell is labeled A squared, on and on. That one shouldn't have A, that should be 1. Okay, yeah? Oh, you're right. That's not the same N. 2 N's mean 2 different things. Let's make this one M, because I already wrote N a bunch of places. N equals the number of M cells. Good. I did mean 2 different things by those N's. Okay, great. Okay. All right, so now we can form like the chain complex like we would if we're computing the homology of this. Okay, so let's just do that. Okay. Okay, so we can form a chain complex. Okay, so I have like C2 of X tilde. This is upstairs space. Goes by my delta 2 H2C1. Okay, and notice that my group ring acts on each of these. Okay, and actually acts on the whole picture. This is all group ring invariant. Okay, so this is these chain complexes are ZG modules. Okay. All right, so now what I'm going to do is just like we went from the group ring to L2, we're going to go from thinking of like finite chains with say integer coefficients to infinite chains, but I want the coefficients to be L2 summable. Okay. If I have okay, so definition. G countable group. Okay, and X tilde is a free G CW complex. Okay, so there's right here, different books will have different notations. Some people will write it as X tilde, some people will just write it as X. I'm gonna follow Clara Lowe's notation. So I'm gonna write this L2 chain complexes, and I'm gonna say G acting on X tilde, okay? Because it depends on G. It's a ZG module. Okay, so I'll try to write this every time. This is just defined as L2 of G. And so project, so both of these are ZG modules with this, the regular cell chain complex of X as I described right there, because this is a ZG module and this acts on it. Okay, so this effectively, this is a lot of algebra, but it effectively labels the elements there. So here's an example of an L2 chain, which isn't a cycle, but I'll just, right, so I could have in my example that we just had, L2, this is like a 1 chain. I could have this one labeled 1, this one labeled 1/2, 1/4, 1/8. So I could look at like the element of L2 would just be 1/2, or like 1/2 to the n, a to the n. Okay, if this is a, that one's the one labeled a, that's a squared, which is sort of like this. Okay, this is a squared, a to the 4th, and then it would just be times this element here would just be whatever this edge is. And so product like this edge. Okay, so I took this edge and I looked at its orbit and I labeled it with an L2 summable. Okay, there's only going to be finitely many possible edge classes, so I can always write as that might be more than one edge class, but there's not going to be that many. There's be finitely many in particular. Okay. Okay, so, and then the boundary operator, let me put the boundary operator over here. The operator 2. This just equals the identity tensor, this other boundary operator. Okay, so now what is the L2 homology? So the reduced, although I've never worked with anything else, the reduced L2 homology of G acting on X tilde. And keep in mind, sometimes people write X tilde, sometimes they write the quotient space, is H2n of G acting on X tilde. This is defined as the kernel of this Bn2. Okay, so this L2 boundary modulo the closure of the image so that I get a Hilbert space. Because I can take the quotient. Okay, so that's the homology. Okay, and the nth Betty number of x tilde, okay, which we're just going to call Bn2 of G acting on x tilde again, is just going to equal this. So now the von Neumann dimension comes in. But in practice, all you really need to know is that it's 0 when the vector space is 0 for our applications. We'll have the dimension Rg of H2 and of this G acting on x tilde. Okay, so this is a Hilbert space, and it's great. Okay, let's have some properties. It's really hard to work from the dimension. Yeah. Yeah. So I'm just using this notation to keep G in the game. That's right, yeah. Yeah, so it's the vector space, so it can change. It'll actually change with finite index subgroups. So you can have different groups acting in the exact same space, and the homology group, the dimension will be different. Okay, so it's a way of organizing the space. I just want to keep track of the G. Okay, so G is important. Okay, so let's just say some properties, some facts. And at the end, I'll give you a bunch of references, some facts. So, and hopefully next time we'll get some more motivation for why this is so useful. Okay, so here's some very nice. If I have x tilde to y tilde with G acting on both of them, is a G homotopy equivalence. Of proper finite type GCW complexes. So for example, if I had two k pi 1s, they're going to be homotopy equivalent. If I look at their universal cover, they'll satisfy this property. Okay, then Bn2 of G acting on x tilde is going to be the same as Bn2 of G acting on y tilde. Okay, so that's great for all n. Okay, let's look at the 0th L2 Betty number that can tell. So this is going to be meaningful to us in terms of like groups. Okay, so if we have two k pi 1s and we look at the action of G on their universal cover, it is, yeah, question?
Yeah, so when you say, what do you mean by the dimension of the time? So how are elements of the L2 homology
Yeah, so this is,
acting on L2G?
yeah, so this is like, so this embeds into like L2G to the N. I'll have to think about how it does that, but it's certainly like L2G invariant, like the whole thing, the whole picture is going to be invariant. So yeah, I'll have to think exactly how that happens, but let me get back to you about that. Let me finish this. All right. Okay, the 0th L2 Betty number. Okay, so let X be connected non-empty proper finite type GCW complex. Okay, then the first Betty number, and this will follow from some other things I'm going to say in a second, of G acting on X tilde just equals 1 over the size of G. So this is going to be 0 if G is infinite. So 0 if G is infinite. All right, let me give you a little bit of intuition about that. Okay, let's look at Z first, and Z, I'll kind of do it for Z, and that'll sort of tell you some things about the general infinite case, because in an infinite group, you're going to have like an axis of z. So let's just look at z again. Zero, I'm going to have this d2 of C12 of z acting on, I'll just call this x tilde. I'll call this x tilde. Make some more space for myself. Okay, so there's no two cells. Okay, and this is also going to go to z1, z0, 2 of z acting on x tilde, which then goes to 0. Okay, so as before, like the example we did, this the quotient by this action just has one cell. Okay, so this is just going to be a copy of L2z. And this only has, the quotient only has one 0 cell, so this is also going to be a copy of L2z. Okay, where you take the boundary just like you normally would, you just notice the labelings. All right, so let's see what these maps are. So I claim that the first kernel, so remember, H1, 2 of x tilde just equals the kernel of D1, 2 all over the closure of the image. Okay, but I claim this kernel is empty. So there's no cycles here. Okay, that's just because if I had a one cell that had a non-zero labeling, so suppose there was just some one cell, I won't even worry about what it's called, with some labeling. If I wanted its boundary to be trivial, okay, so now I've got oriented, so I haven't been orienting things, but I've oriented cells. If I wanted its boundary to be trivial, I'm going to need, so the boundary of this, whatever group element this is labeled with, the boundary is this vertex with its labeling minus this vertex with its labeling, which are different labelings. Okay, so I'm going to have to add in a 1, and then I'm going to have to add in another 1. Okay, so this is not L2 summable. Okay, so whatever value this is, I'm going to have to add the same value everywhere else, because that's the only way I can get rid of those endpoints. And so that's not going to be not L2 summable. Okay, so this is 0. Okay. And that the first homology is 0. I'm going to leave as an exercise to do the exact computation, but I want to say that the kernel, okay, so what is L0 2 of G acting on x tilde? Okay, this just equals the kernel of this epsilon map. I might not have labeled it, but that's everything all over the closure of the image of 2. Oh, sorry, D1, 2. Okay, so I want, epsilon is this map, I didn't label it. It's the map to 0. So the kernel is everything. Okay, and then, so I want to claim that the image of delta 1, 2 equals all of L2 z in this case. It's the whole thing, in other words, which will also make this trivial. So how can I do this? So I suppose I have one vertex that I want to make trivial. Okay, so suppose it's just labeled 1. Again, I'm going to have to do this. So it's not going to be directly in the image, right? Because I need to get rid of that. The only edge that has this vertex there is this edge right there. So I have to add that edge. And then if I want to make this in the image, okay, so now this has boundary 1 on this vertex minus 1 here. I've got to add another edge here, 1, 1, 1. So that's not going to work. It's not in the actual image. So the vertex 1 is not in the image, but it is in the closure of the image claim. Okay, so let me just give the general idea. What you can do, this is, I'm not giving the whole proof here because you need to find some sequences. They'll take 1, I'll take 1 here. Okay, and now what I'm going to do is I'm going to take something that's just like 1 minus epsilon 1 here. Okay, so that means now when I take the boundary, and I'm going to keep going, and I'll do like 1 minus epsilon 2 here, and I'll keep going so that the boundary of this new thing is now going to be 1 here, and it'll be epsilon 1 here, and epsilon 2 here, and so on and so forth. And I want to get this, I want a sequence of these things that converges to 1. Okay, so what you want is to get a sequence of L2 summable things that converges just to that. So its boundary becomes 1. Okay, so it's not, so I thought this was interesting because it's not actually in the image, but it's in the closure of the image. And also this shows you a general idea why an infinite group has 0 first L2 Betty number, because any vertex, if it's an infinite group, you can take a ray going away from it and do a similar sequence of things to get what you want. Okay, so now we can talk about L2 homology of groups because of what I'm already saying. Yeah, question?
So you said the Betti numbers in this case are
Yeah, that's right.
are the homology modules, not G modules?
Probably. I'll have to think about that. Okay, so, but the main thing is it's going to be like L2 to infinity, you know, like as, it's just how you organize them with G modules. So, and you might have different, so like you could have one with a different number of orbits of n cells. Like when you quotient down, you could have a different number of cells. So they'll be labeled differently. It's not necessarily going to be an obvious map there. So you might have different number of orbits in one from the other, and still their Betty numbers are the same. I mean, the actual homology groups will be infinite dimensional, but what the G does is it just organizes them and to give you the dimension. Okay, so I'm about to use this fact that I'm erasing the definition of a group because it doesn't depend on the G equivariant homotopy type. G accountable group. Finite type group. Then Bn to just of G just equals Bn2 of G acting on K pi 1, the universal cover. Okay, G1, the universal cover. Okay, so I take a classifying space for the group. I look at the universal cover. It's a free G CW complex. I take the Betty numbers of that, and that's the Betty number of my group. And from the thing that I just erased here, it doesn't depend on the homotopy type of the classifying space. Okay. Oh, and I wanted to show you, so you haven't seen an actual, maybe I'll show you that cycle later. I want to show you an actual cycle in a minute. Let me continue with more properties. Okay, so 3. So this is the L2 Betty number of a group, which is what we'll kind of use in geometric group theory. So let me some properties. Okay. Okay, dimension, you probably can guess this, but if G admits a finite model, which is what most of the time, so you actually have a finite number of cells, like in Z, a finite KG1, of dimension n, so that's a maximal dimensional cell. Then Bn2 of G is 0 for M bigger than that dimension. Okay, so when you don't have any cells, you get 0, which we've sort of been using before. Okay, and then an important property, what I was saying about the subgroups, this restriction property. Okay, if I have H, a subgroup of finite index, again, G is countable and finite type. And then Bn2 of H. Okay, so now I can just write the group here by my definition over there, just equals the index times B2 or N of G. Okay, and so, yeah, so this is a handy fact that comes in. So this is like the re-indexing of the homology classes. Try this. All right, and let me just say one more fact that'll give us the free groups, and then I'll show you the, there's kind of a Konneth formula. Okay, so for n equals 1, I can look at, where's all this? N equals 1, I can B1, 2, G1, free product G2, just equals B1, 2 of G1 plus B1, 2 of G2 plus 1 minus B0, 2 of G1 plus B02 of G2. Okay, so this comes from, you can sometimes, be very careful, use Meyer-Vietoris. Okay, but you have to be very, very careful. Okay, so here it's just a free product. Okay, so it's okay, the group structure is nice. Okay, so let's think, let me just write it for n greater than 1, and then we'll be able to do the free group. Bn2 of B1, B2 equals Bn2 of G1 plus Bn2 of G2. So what does this give us for the free group? Because we did it for Z, right? So a corollary here, we'll see another way to get the free group. B12 of F2, which is just B12 of Z star Z, okay, just equals 1, okay, by this. So this is like 0 plus 0 plus 1 minus 0. Okay, and B12 of Fn equals n minus 1. Okay, so let's look, so let's see if we can see this as a non-trivial. So this should have a non-trivial cycle. So let me show you that non-trivial cycle, or show you some. So we've seen spaces that don't have any cycles, but trees do. And a lot of times the cycles that you find are coming from this way. Maybe it's natural, maybe it's because it's the only way we know how to find them. So I'll just do trivalent tree, but you could do this. You could put this in the Cayley graph of F2. Okay, so I can label this edge with 1, say. And these edges with 1/2, 1/2. And these with 1/4, 1/4, 1/4, 1/4, and so on, 1/2, 1/2. Okay, and you see that the boundary is going to cancel out everywhere. This says this cycle has no boundary. Okay, and then the squares, it's square summable. Okay, so like these are going to be like 1/4 plus 1/4, so that'll be 1/2. These are like 1/16, 4 of them, so this will be like 1/4, and I'll have like an 1/8. Okay, so this is a square sum, and adding up this part's fine, same as this. Okay, so this is a square summable sequence, which is a cycle. Okay, so you can maybe believe combinatorially a little bit that this has non-trivial first Betty number, at least that it has a cycle. And the one thing I'd like to do is try to understand how you can get the cycles like representing classes, or just understand it better a little bit combinatorially. Okay, let me say just a few more facts. There's many facts. Okay. The fact that we like from homology is Poincare duality. It's really useful. So let's have that. Poincare duality. Okay, if G admits a finite classifying space, which is that is an oriented, closed, connected D manifold. I'll stop using N. Okay, then B into of G. Okay, so this is the fundamental group of the manifold. Okay, is equal to B2 of D minus N of G. Okay, so we can use this to do surface groups. Did I say the thing about Euler characteristic? I did not. Okay, so the Euler characteristic of the group equals the alternating sum. Again, countable group, finite classifying space equals the sum, -1 to the n times B in 2 of G. Okay, and you can also use this to recalculate the Betty numbers of the free group, which we just did. I won't do it again, but you can use this to get a calculation of the Betty numbers of the free group. And also we can get a surface group this way. Okay, so let G equal pi1 of SG. Be bigger than equal to 1. Okay, so the 0th Betty number, 0, 2, pi1 of SG, is going to equal 0 because it's infinite group. Okay, and then by Poincare duality, I'll have, because this is a 2 manifold, I'll have the is also going to equal 0. So then by the Euler characteristic, this B02 of pi1 of SG just equals the negative Euler characteristic of the surface. Okay, so it is very helpful. Okay, so we've actually computed a fair number of groups. Let me say, since I did surfaces, let me just state what happens for manifolds. Say it again. Oh, this should be 1, thank you. Thanks, good eye. Okay, so for hyperbolic, so L2 Betty numbers in this combinatorial form, so they were first done completely using analysis. And so they could do it for smooth manifolds. A lot of work has been done on smooth manifolds. So for hyperbolic manifolds, and I don't just mean manifolds with word hyperbolic fundamental group, I mean Hn mod gamma, where this is some discrete group of isometries of Hn. If D, make this D odd, we'll have B into gamma is going to equal 0 for all n and n. So gamma equals pi 1 of a closed hyperbolic 3 manifold, real hyperbolic 3 manifold. Okay, so you notice this might be wrong in even dimensions because of the Euler characteristics of D even. Then B into is going to equal 0, except for n equal to D over 2, where it's not 0. Yeah, closed hyperbolic, thank you. Okay, but it's not the same n, closed hyperbolic D manifold. Thank you. Where it is non-zero. Okay. So as I was saying, so originally, I haven't said any names at all, I don't think. So ITEA, my understanding is that it originated understanding like smooth structures. So it was very analytic. And then later, it was realized in this combinatorial way, which I find very interesting, at a combinatorial description. And then there's a singular version. So a lot of work was done by Cheeger and Gromov. So I think it's just becoming popular more in like combinatorial group theory recently. And oh, I wanted to say, so obviously I'm not an expert, but I have some sources. And those sources, which I think are very good. Well, there's Luke's book, which you're supposed to say. Okay, and it's very long, but there's also shorter treatments. There's one by Clara Lowe, and there's also one by Kemmeyer. And I'm happy to share those with you if you want. Okay, and I'll end there. I have 1 minute left, and on my next talk, I'll talk about some applications. I think I talked about all this. I'll talk about some applications and how it might relate a little bit back to what we were talking about on Monday.
Any questions?
Okay, sorry. Oh yeah, there's been a lot of work done with amenable groups. Minicourse. Yeah, there's like a duality, like there is. Yeah. Mm-hmm.
Any other questions, comments?
Is this L2 homology stronger than the usual singular homology in the sense that can it detect any differences in cases in which the singular
Well, so like if
homology
I'm
coincides?
I erased my Z example, but like up here, like so for example, this tree, the homology is going to be trivial. It's like straight up homology. Okay, and so what ℓ2 homology does that I find useful is that it takes a space that maybe has no intrinsic homology and looks at the group action on it. So it's kind of like the homology of a group action. That's why I like this notation G acting on X. It's like the homology of a group action.
Any other questions? Yeah, so if it's 0, then that means that the actual homology of the space, like the H2 of G acting on X, is 0 as a vector space. So that's very strong. So the dimension, so that means that there's no like either this, you can sometimes figure that out combinatorially. And so when it's 0 and you have like a cat 0 cube complex or some Riefers group, you're going to be able to say things about the group structure. That is helpful to understanding what's going on. And also that's a quasi-isometry invariant, whether it's 0 or not. So that really relates to geometry group theory. So I feel like the 0, non-zero is like the main thing to try to understand. Yeah, that gives you, yeah, the other ones give you important stuff. I'm just working on 0. Okay. Any other questions? If not, let's thank the speaker again.